we go. You ready?
Sounds good.
The broadcast is now starting. All attendees are in listen-only mode.
Hello, welcome everybody. Coffee with Caleffi. A crowd pleaser today. We've got John Siegenthaller, a friend and an associate in the business, is going to do the presentation. I think this is going to be a very interesting topic, and we're actually going to jump right into it. I've got some housekeeping that we'll save for the end, but type in any questions you have. We'll try and get to those also as we go through here. And without further ado, John, take it away. Thanks for coming, too.
Yeah, thanks, Howard. Glad to be with everybody today. We put together this Coffee with Caleffi around two types of heat pump systems, air-to-water and water-to-water heat pump systems. They're both broad topics. We're going to look at some of the essential information. We're going to look at how to interface both those types of heat pumps with some modern hydronics technology. And then we'll look at some schematics. We'll take some questions at the end. So, some basics. We'll start off with the air-to-water heat pumps. These are a lesser-known type of heat pump currently in North America, but you'll see globally they're widely used by the hundreds of thousands. We'll look at some of their thermal performance characteristics, some design examples. Then we're going to move over to water-to-water heat pumps, specifically geothermal applications of water-to-water heat pumps. Again, we're going to look at performance characteristics. We're going to look at some different types of earth loops, traditional earth loop construction as well as manifold-type earth loop construction. And finally, we'll wrap up with a couple systems up with some modern hydronics technology. I do want to mention a publication that is available through Caleffi called Hydronics. I'm sure many of you that are in attendance today have seen these. Right now there are 14 issues out. Issue number 9 was titled Geohydronic Systems. That is the reference issue for information today. And then coming up in July will be the next issue, number 15, which is on separation in hydronic systems. If you've not seen the publications, the website here, you can sign up to receive both a hard copy as well as download PDF files of hydronics. Okay, I won't spend too much time on it. I think most people that are attending today have got the basics of how a vapor compression refrigeration system works. Both the heat pump types we're going to look at are reversible heat pumps. They have a reversing valve that essentially swaps the function of the two heat exchangers that are involved. In the heating mode, over on the left side here, we're looking at heat absorption into the evaporator, cool refrigerant evaporating, and after it passes through the reversing valve up to the compressor and down to the other heat exchanger, which in the heating mode is functioning as the condenser, and that's where we're dissipating heat off to the load. When we apply a 24-volt signal to the reversing valve, basically the function of the evaporator and the condenser are swapped. And again, both types of heat pumps will use that. So let's get into air-to-water heat pump systems. I mentioned this is a lesser-known type of heat pump in North America right now, but a slide that's coming up will show you there are many manufacturers of these products globally, and I'm sure you'll recognize a lot of these manufacturers. This happens to be a Daikin unit. This is available in North America. There's a couple flavors that Daikin offers. In this case, we're looking at what's called a split system, where we have an outdoor unit here in the upper left and an indoor unit. These would be connected by a refrigerant line set that you see down here. One of the benefits of a system like this, a split system, is that there is no water in the outdoor unit, only refrigerant. So we don't have to be concerned about freeze protection in cold climates with that. One of the disadvantages is you do need a refrigerant technician to properly install this, make sure that line set is connected right, and that you have the proper charge in there. The indoor unit typically has it has a refrigerant to water heat exchanger, which in the heating mode is going to be the condenser. In the cooling mode, it would be the evaporator. Most of these units, indoor units, also have a circulator and sometimes an expansion tank. The other type of air-to-water heat pump is usually referred to globally as a monoblock style heat pump. I call it a complete unit. It's where the entire refrigeration system is self-contained and pre-charged. We've got a couple examples here. Again, a Daikin unit up at the top. This is another unit down at the bottom from SpacePack that is currently available in the North American market. When we're dealing with this type of a system, we are going to be passing either water or a water antifreeze mixture between the outdoor unit and the balance of the system on the inside. Now, in a warmer climate where you have infrequent freezing, southern climate, perhaps southern Midwestern climate, southern European climate, these systems are set up with just water. They do have some freeze protection mechanisms in them. For example, when the outdoor temperature drops below typically about 40 degrees Fahrenheit, they'll automatically turn on the circulator inside the heat pump and create circulation. Some of them also have an electric resistance heating element that will come on at a certain temperature. But ultimately, in a power failure, the only thing that can prevent it from freezing is antifreeze. So this lower schematic shows a system where we're tying the outdoor unit to a brazed plate heat exchanger, and we are using an antifreeze fluid between that outdoor unit and that heat exchanger. Some manufacturers mandate for these units, again, in a cold climate where you have frequent freezing, sub-freezing conditions, this is the preferred installation technique. Internal components, again, it's a basic refrigeration cycle. The difference between this type of heat pump and a water-to-water, at the top of the unit here, we've got an air-cooled condenser in the cooling mode or an air-heated evaporator in the heating mode. But the other basic components are all pretty much the same. Okay, now I mentioned some of the products that are available have internal components, internal system-related components like a circulator and an expansion tank. The Daikin unit is one example of that. Other units don't have any internal circulators. So we have an external circulator. Excuse me. This lower schematic shows a typical setup where we've got a heat exchanger, purging valves, air separator, circulator, and because this is now a closed hydronic loop, we do have to have an expansion tank on there. One other component I'll point out right here is a flow switch. The flow switch is in there so that we don't accidentally freeze up that heat exchanger. If we're in a mode where we're extracting heat, we're in a cooling mode, that cool fluid coming in there, especially if it's an antifreeze, could be below 32 degrees Fahrenheit and potentially could freeze that up. So some control systems are set up so that the heat pump can only operate once flow is verified using a flow switch. Some units build that flow switch in, other units need an external flow switch. Over here on the right is a really nice looking installation. This was done by Revision Energy up in near Portland, Maine. It shows an alcove that's been built that basically keeps some direct precipitation off of those units. If it's facing south, it might even create a little bit of a microclimate effect there. It also elevates the outdoor units up above the snow line, so it's a nice setup. Now here's a unit that, to my knowledge, is not available from any manufacturer currently in the U.S. This is an interior air-to-water heat pump. And you probably get the idea from these lower photographs what's going on here. We've got a couple louvered panels outside, and you see those large flex ducts. One brings outside air into the unit, and for example, if the heat pump's in the heating mode, the heat is extracted from that outdoor air, and then it is sent back in, sent back out through the other duct. Sorry about the phone here. I'd love to see a manufacturer create something like this. I kind of like this idea because it keeps all the circuitry inside the building. If you have to service this unit, the compressor and all the electrical circuitry is serviceable from the inside of the unit, inside the building. Here's one other idea. I thought this was a very unique product and wanted to show it today. This is a unit that is built up in Canada by a company called Thermodynamic. And what this unit is essentially an interface module. This company recognizes that there are many condenser units that are built by the large air conditioning manufacturers like Carrier and York and Trane and many others. So rather than compete and try to build a competing condenser unit, they build an interface product, which essentially has a refrigerant line set that goes out to an outdoor condenser unit. And inside this unit is piping that interfaces to a buffer tank. You see the electric boiler right here as a backup. And it also interfaces to low temperature hydronic radiant panel distribution systems, as well as an air handler. This unit is set up so it can do heating as well as cooling. And in particular, in the cooling mode, it can use the radiant panel for sensible cooling, and it can use the air handler to do the latent cooling or the moisture removal. You'll see inside the unit here there's a mixing valve circulator, there's a coaxial heat exchanger, and it's pretty well thought out design. Here's an example of how the unit would operate in the heating mode. We would have the condenser unit up here. These orange pipes represent the refrigerant line set that comes in to the coaxial heat exchanger. The heat that's being produced is sent off to a buffer tank. And then from the buffer tank, it can be supplied through this combination diverter valve, mixing valve assembly. It's one valve, but it can function as both a diverter valve or a mixing valve. But in this heating mode, it's functioning as a diverter valve. It simply sends this hot water from the top of the tank out towards the load. If there's a temperature boost necessary, the electric boiler can do that. Goes off to the low temperature. In this case, I'm showing radiant ceiling panels. Could be floor panels, wall panels. And then it comes back and goes back to the buffer tank. So the buffer tank allows you to have a highly zoned distribution system and not short cycle that refrigeration system. Now the next slide shows this in a cooling mode operation. So our outdoor unit is the condenser. It's rejecting heat. It's chilling down the water in the buffer tank. And there's two loads that chill water goes to. The coolest water goes directly to the air handler, so we can get good coil performance, latent cooling, moisture removal from the coil. And then some of the cool water also comes down through this three-way valve. Now, in this cooling mode, that valve is operating as a mixing valve, and the logic that's operating it is dew point control. So there are sensors that are looking at the indoor air temperature as well as the relative humidity, calculating dew point, and operating the actuator of that valve so that the water temperature leaving that valve and going out to the distribution system is a few degrees above the current dew point of the room. So we can do radiant cooling as well as some forced air for latent cooling. It's a well thought out product. Website is down there if you want to take a look at it. Let's talk a little bit about heating performance. With any heat pump, the difference between the media that we're extracting heat from and the media that we're sending that heat to, the closer those two temperatures are, the better the performance of the heat pump. That's true for both heating capacity, the BTU per hour transfer rate, and it's also true for the coefficient of performance. You can see that as the outdoor temperature goes up, our heating capacity goes up very steeply, and also as the outdoor temperature goes up, the coefficient of performance goes up. And ideally, we'd like the highest capacity and the highest coefficient of performance. Now, we obviously can't control that outdoor temperature. We can control, though, to some degree, the water temperature going off to the load. And we do that by the design of the distribution system. The lower the temperature that the distribution system can operate at and still provide the necessary heat output to the building, the better the performance of the heat pump is going to be. So when we think about heat pumps and hydronics, we always want to think around low temperature hydronic distribution system. Radiant panels, possibly some low temperature thin tube baseboard, some low temperature panel radiators. The criteria I'd like to suggest on a design day, supply water temperature no higher than 120 degrees Fahrenheit. So again, if we look over here on the left, we're basically taking heat from the outside air and we're going to put it into water that's going to carry that heat off to the load. I call this the temperature lift between the outside air and that load water. The lower the lift, the better the capacity and the COP of the heat pump is going to be. Cooling performance. Well, it's really the same idea in the other direction. The cooler it is outside, and the warmer the water temperature that is serving the cooling distribution system, the higher the cooling capacity and the higher the energy efficiency ratio is going to be. Again, we don't control the outdoor temperature, but we do have some control over that chilled water temperature. Traditionally, chilled water systems are designed around 45 to maybe 50 degree Fahrenheit supply water temperatures. I mentioned radiant panels. One of the nice things about using a radiant panel for sensible cooling is that we can bring that temperature requirement up, often into the mid to upper 60s, at least for part of the load. And this helps us with higher cooling capacity and higher energy efficiency ratio. So again, if we look at it from the standpoint of temperature lift, we're taking heat from the chilled water and we're dissipating that heat to the outside air. So the less this temperature lift is, the better the performance of the unit is going to be. Now, when we look at an air-to-water heat pump, in terms of sizing, typically most air-to-water heat pumps are not designed to handle the design heating load of the building. Some of them do have supplemental heat strips built into them, maybe a 6 kW electric heater. And what this graph is showing here, I call this a heating duration curve. It shows the number of hours in a year when the space heating load is at or above a certain percentage of design load. Here's design load conditions up here. You can see the number of hours in a year, and this graph is pretty coarse. It goes from 0 to 5,000 hours. But the number of hours in a year that we're at or close to design load is very small. And it doesn't really make sense to size the heat pump for that condition because it would be pretty oversized for the balance of the year. And you're installing a more expensive unit. You're going to cause some operational problems like short cycling. So a reasonable compromise is to design that heat pump around perhaps 75 to maybe 85% of the total energy supplied over the year. If we look at this graph, that blue shaded area would represent a pretty high percentage. If you look at the total area under this black curve, the blue shaded area is a high percentage of that, perhaps 80, 85% of it. The orange shaded area represents the energy contributed by the supplemental source. It could be an electric boiler, it could be some other type of a boiler. And then this pink shaded area over here represents the spare capacity of the heat pump. And this just shows that at some point we're going to bring some supplemental heat in, and we're going to boost the total heat output going to the load based on that combined output of the heat pump and that boiler. Another possible operating mode is where we get down to some minimal outdoor temperature, which is low and occurs relatively infrequently. And at that point, we're simply going to shut the heat pump off, and we're going to rely entirely on a supplemental heat source to carry the load. So you see the difference here is that for a few hours out of the year, and I'll throw a number out, maybe 20 to 50 hours in a year, the heat pump is shut off. Perhaps it's -10 outside. Now, some heat pump can actually operate at those conditions, granted at low capacity and very low CLP, but in some cases it simply doesn't make sense to strain the refrigeration system in the heat pump at these very low temperatures for the amount of heat that's coming out and for the duration of time that these temperatures exist. So the control logic might be simply shut off the heat pump and use all supplemental heat. So basically, as you look at these graphs, what you're trying to do ideally is maximize the blue shaded area as a percentage of the total area under this curve. And as I say, a good target in that is to provide maybe anywhere from 75 to 85, maybe even 90%, depending on climate. And you can do studies with thin temperature data and examine this. But keep in mind that you're going to have that supplemental heat source. And of course, that supplemental heat source is nice from the standpoint of being a backup. If that heat pump is offline for any reason, you've got some partial heating capacity available to you. Now, I mentioned earlier that some of the heat pumps that are available, and this is typical of a European and an Asian type of product, some of them build in components that in North America we tend to view as components that the installer would supply, things like circulators, expansion tanks, and so forth. So in some cases you've got an indoor unit with a built-in expansion tank and circulator, and what I want to caution you on is a couple things here. One is, don't assume that that built-in expansion tank is large enough to handle the expansion requirements of an entire system. It really wasn't designed around that. You may have to supplement it with another expansion tank, especially if we have a high volume distribution system. Imagine several thousand feet of floor tubing. You might have 50 gallons of water there, and the expansion volume of that amount of water may necessitate another tank. So you want to take a look at that. Take a look at the size of the tank that's in that unit and see if it can handle the system. If it's a very small distribution system with perhaps 5 to 10 gallons of water in it, that indoor unit, the tank that's built in, will probably handle it. If it's a larger distribution system, supplemental. The other thing I want to mention is don't assume that the circulator that is built into that unit can suffice to push fluid through an entire distribution system, especially if it's an extensive radiant panel system. We like to talk about the net pump curve. If we look at that circulator, and these are typical circulators, small wet rotor circulators, the red curve here would represent the pump curve of the circulator. The blue curve represents the head loss of the components within the, in this case, the indoor unit of the heat pump. That water has to flow through piping, it has to flow through heat exchangers and valves, and of course that dissipates heat, or excuse me, dissipates head. So the orange curve here is basically the red curve minus the blue curve. It gives you the, in effect, the net pumping ability of that unit towards an external load. If, again, we have a small primary loop that we're pumping into, the internal circulator will handle that. If it's a large distribution system, you're better off to couple that indoor unit to the distribution system using some form of hydraulic separation. It could be a buffer tank, closely spaced tees. It could be a hydraulic separator. You'll see some of that in the schematics. Now, I'm subject to buffer tanks. Anytime we have a highly zoned hydronic distribution system and we have an on-off, or in some cases even a modulating heat pump, the question at hand is really, does the heat pump have the ability to reduce its heat output low enough so that if one of the small zones is operating, and that's the only zone that's operating, that the system is stable? Or would the system get into a short cycling situation? And in general, when we look at heat pumps, many of them are simply one stage, on or off. Some of them are two-stage. They have a better ability to match capacity. But if we had, as shown in this schematic here, if we had 8 zones and we had just one of those smaller zones operating, the heat pump simply can't reduce its capacity low enough. So we're going to be into the same situation that we would have with a boiler. We're going to have the heat pump short cycling as it produces heat, and simply the load can't take that heat as fast as the heat pump is producing it. So what do? We put in a buffer tank. Now, Caleffi makes a nice tank here. It's got a lot of generously sized, well-placed connections, and the schematic here shows an example where the outdoor unit is set up with an antifreeze circuit to a heat exchanger. From the heat exchanger, we're going right into the buffer tank. The buffer tank here is actually acting as a hydraulic separating device between this circulator and potentially a variable speed circulator over on the distribution system. And even though it serves as that hydraulic separating device, that's not its primary function. Primary function is to buffer. If you want to calculate size of expansion tanks, it's a pretty basic formula. We look at the heat pump output minus any load that might happen to be on at the time. Generally speaking, the heat pump won't be on unless a load is on. That, of course, depends on your control wiring, but generally, heat pumps are not set up to just maintain the temperature of the buffer tank. They're going to be turned on based on the demand for heat. So if we took the smallest load that might be on, this is essentially the net BTUs per hour that has to go into storage. T here represents the number of minutes that we'd like that heat pump to operate once we turn it on. I would suggest a 10-minute minimum to you. Again, you can use the formula experiment with other times. Obviously, the longer you want that heat pump to stay on, the bigger the buffer tank's got to be. And the bottom here, this is a constant based on water, and then the delta T is the temperature rise in the tank from when you turn it on to when you turn the heat pump off. Now, with the heat pump having limited temperature range, this is the upper end of this, probably for most heat pumps, not all, but for most, will probably be about 125 degrees Fahrenheit. The lower end is going to depend on the design of the distribution system. The lower you can make that distribution system operate in terms of water supply temperature, the wider this delta T can be, and the smaller the buffer tank can be. Now, I mentioned earlier that.
Hey, John, this is Mark. Back to that prior slide. One question, please, that came in. On the system side, is there an expansion tank that needs to be included in the schematic?
Good eyes. Yes. There has to be an expansion tank. It's not fully detailed. Absolutely. You'll see there is an expansion tank over here on the antifreeze side of the system, but the water side of the system does need to have an expansion tank on it. Okay. There is a publication called JARN, J-A-R-N, Japanese Air Conditioning, Heating, and Refrigeration News. And back in August 2013, they put out an issue that more or less detailed what the status of the air-to-water heat pump market is worldwide. And I happened to get a copy of this, and I was quite surprised at the numbers here. In 2012, the global market for air-to-water heat pump systems, almost 1.4 million units were sold in 2012. That year was up 5.4%. If we look at some of the other statistics that John cited here, the European market, 181,000 units sold in 2012. The major markets, France, Germany, and UK. Take a look at China, almost 700,000 air-to-water heat pumps. Japanese market, 454,000. Even in Switzerland. Now, this isn't an annual figure. This is what they're targeting for installed air-to-water heat pumps by 2020, based on a renewable energy portfolio. To contrast with that, take a look at, and this is an estimated number for the U.S. market. This is not based on actual sales statistics, but JARN estimated in 2012 about 1,000 units. So you can see that the U.S. market is far, far behind the European market as well as the Asian market in terms of these products. But hopefully that's a situation that will change because the physics really is the same. Now, I want you to take a look. I copied a couple schematics here. I just pulled these off the web from a couple companies I'm sure you'll recognize. Mitsubishi. Here's an air-to-water heat pump system, integrated buffer tank, hydraulic separator, low-temperature panorads or floor heating. Also some domestic water coming off of that unit. Here's another competing system. It's a split system from Panasonic. And if you do a little research on Google, you'll find that many of the other big names in air conditioning, Fujitsu, Samsung, so forth, all have these units in the other markets, but have not launched those products into the North American market at this point. I suspect that that will come about at some point. I certainly would like to see it because there are some decided advantages of these products. Geothermal is a great technology. We've used it. It's not the right fit in every case, nor is an air-to-water. But when you look at different circumstances, such as very limited land area, air-to-water heat pumps have got some advantages. Now, I want to show you a quick performance, kind of a cost comparison between a geothermal heat pump and an air-to-water system. It is simply a snapshot. It's a given set of assumptions. It doesn't apply everywhere, but I'll give you a quick orientation. Let's take a house in Syracuse, New York, upstate New York, fairly cold climate, about 6,700 degree days. Let's say that that house is a nominal 3-ton design load when it's 70 inside, 0 outside. Total estimated heating energy is about 50 million BTUs per season. Right now, the cost of electricity in Syracuse averages about 13 cents a kilowatt hour. And let's assume that we're going to set this house up with a low temperature radiant panel, floor panel, perhaps a ceiling panel, that at design load conditions can operate at 110 degree Fahrenheit water temperature. So what I did is I used some manufacturer software to simulate the operation of a heat pump. And in this case, their particular model that would cover this load was a 4.5-ton split system unit. Their software estimated a seasonal coefficient of performance of about 2.8. Estimated installed cost, excluding distribution. I'm looking at this from the standpoint that the distribution system is going to be there with either the air-to-water heat pump or the geothermal heat pump, $10,600. Now, here's the geothermal option. Again, I use manufacturer software. I ran the simulation, and seasonal COP almost 3.3. So you can see if you compare the COPs, 2.8 versus roughly 3.3, it's no question the geothermal system has the higher COP, but I want you to remember you don't pay for COP. You pay for kilowatt hours. Let's take a look at the installed cost. The earth loop, let's assume that it was a vertical bore earth loops installed, almost $12,000. The balance, including the heat pump and the mechanical room piping and so forth, about $8,800. And again, not including the distribution system, we're at about $20,500. Now, currently there's a 30% federal tax credit. I took that tax credit off on it because the geothermal heat pump does qualify for that. So our net installed cost is a little over $14,000. Now, let's look at operating costs. The air-to-water heat pump system with that average COP of 2.8, about $676 a year. This is a fairly energy-conserving house in a cold climate. The geothermal with the higher COP was roughly, well, just under $100 less per year. Okay? If we look at the difference in the net install cost, almost $3,800, and if we look at just simple payback, essentially we're trying to amortize $3,800 additional cost on at least an initial savings of about $100 a year, and you can see that really has a long payback period. Once those tax credits are gone, they're due to expire at the end of 2016, that would make this an even more favorable situation. So again, it's not my intention to knock geothermal. We've done it. There are excellent applications for it. But I also don't want you to dismiss air-to-water heat pumps simply because they do have a lower coefficient of performance relative to geothermal systems. Now, let's look at the balance of the system. What's important? What's important is low temperatures. My suggestion is nothing higher than 120 degree Fahrenheit supply water temperature under design load conditions. And there's a lot of heat emitters that can meet this condition for you. Here's one of them. This is a relatively new product. It's called Heating Edge Baseboard. It is available in North America. If you take a look at the internal construction, you can see that compared to traditional fin tube baseboard, much larger fins and two tubes. It's essentially a larger heat exchanger core inside a similar baseboard type enclosure. Some of the performance numbers are down here. At an average water temperature of 120 and 4 gallons per minute flow rate, we're at almost 450 BTUs per hour output per foot. So again, when you compare the output of this type of baseboard to traditional fin tube baseboard, at a given water temperature, you're getting more than twice the output. But our objective here is not to get twice the output, it's to get the output needed at the lowest possible supply water temperature. So that's one product that's available. Here's a brand new product coming out of Canada, a company called Hydronic Heating Technologies. Their website's down here at the bottom. This was just released in March, and again, if you look at this, it's a baseboard style convector, natural convection, but take a look at that heat exchanger. There's multiple tube passes, lots of fins, deep fins in it. It's essentially a bigger heat exchanger core inside a baseboard type enclosure, nice contemporary enclosure. So based on the numbers supplied from the manufacturers, a little over 500 BTUs per hour per foot at 120 degree water. And it comes in standard lengths. There are trim accessories with it and so forth. So Again, a couple quick examples of some fin tube that's available. Panel radiators can be designed around these low water temperatures, but the key thing is you have to correct the output data. Oftentimes the output is listed for high water temperatures. It's typically listed for an average water temperature inside the panel of 180 degrees Fahrenheit, just higher numbers. But this curve or this formula will give you a correction factor. It's essentially a multiplier. You multiply the output of listed output at the higher temperatures around that, and you'll get the D-rated performance. Down here is an example. If we compare the listed performance around that 180 degree average water temperature, if we drop that average water temperature to 110, we're getting roughly a quarter of the output, about 27% of the output that we would at 180. So you can see it is a severe loss in terms of heat output, and this means you're going to be using larger panels. That's simply the price you pay for efficiency. Here's another unit that's out there from Yaga, North America. It is a deep convection coil with some very small, very low power fans. These fans are there to boost the convective output under low water temperature conditions. They're very low power. At full speed, they're about 1.5 watts each. Very quiet. These are essentially the same type of fans that you find in a desktop computer. You can see the thermostatic radiator valves that are on these. So these operate like a panel radiator, with the difference being a boost in convection at low water temperatures. And that boost is very significant, about a 200% improvement in terms of convective output at those low water temperatures. Here's another unit, similar concept. This is from Runtal. This was introduced a couple years ago. It's called their Neo unit. Again, we've got a fairly deep fin coil element. We've got a rack of low power fans. We have radiation coming directly off the front. Here's a front view of the unit. And we have convection. So just to give you an idea of what performance is, if we look at an 8-tube high panel, that would be this height here. 8 tubes high, just under 5 feet wide, getting about 5,700 BTUs per hour at an average water temperature of 104 in a 68-degree room. So again, these products were specifically designed to go after that low temperature market. They're designed to be compatible with heat pumps, and certainly they'd be compatible with solar thermal, they'd be compatible with mod-con boilers, all of which benefit from those low water temperatures. Radiant ceilings. Here's a photograph of a radiant ceiling system going in. This is using half-inch PEX aluminum PEX tubing. It's using some aluminum-based foam insulation board and some preform aluminum plates. Here's a cross-section. Down here, these are all standard tube and plate products that you can buy. Over here in the upper right, a visual photograph of that ceiling. It's just a standard drywall ceiling with a flat white paint on it. Here's what it looks like to an infrared camera as it's warming up. You see these red stripes. These are indicative of good lateral heat transfer away from that tube. And if you want to estimate performance, here's a formula down here for this particular design. I'll give you a quick example. If our average water temperature in the panel was 110 Fahrenheit and the room was 70, what I call our driving delta T is about 40 degrees under those conditions, times 0.7. Roughly, we're getting about 28 BTUs per hour per square foot from that ceiling, which is excellent output at those water temperatures. Oftentimes, in a well-insulated house, the design loads can be in the range of 10 to maybe 15 BTUs per hour per square foot of floor area. So with this type of a system, you don't have to cover the entire floor or the entire ceiling. You may find that, for example, here, with the 6-foot wide radiant panel ceiling, we're able to cover the entire heating load of a 14-foot wide second-story room. So it's a good system, and it's also one that's potentially adaptable to radiant panel cooling. Same system turned 90 degrees. This is a radiant wall. It's identical construction. The black is just the difference in the tubing manufacture. Again, you can see the infrared photograph here in the upper right showing that good lateral heat dispersion. Here's the finished wall. Visually looks identical to a standard wall. The stairwell we're looking at here, this actually has a radiant panel in these two walls. So radiant walls and radiant ceilings, I like to say oftentimes they're the overlooked radiant panel. Most people think of floors. But with low water temperatures, they're very adaptable into a lot of situations. So if you design around hydronic systems, I definitely would encourage you to take a good look at radiant walls and radiant ceilings to supplement what you already know on radiant floors. Speaking of radiant floors, a slab-on-grade system can work well here. Ideally, we want no finished floor resistance or very low finished floor resistance and relatively close tube spacing. Ideally, 6 to 9 inch spacing would give you relatively low water temperatures, in some cases under 100 degrees Fahrenheit. That's going to be very compatible with that low temperature performance characteristic that these heat pumps have. Now, here is a Combisystem. By Combisystem, I mean we're producing space heating and domestic hot water. I'm starting out here on the left with a self-contained air-to-water heat pump. We're going to assume it's set up with an antifreeze solution between an internal brace plate heat exchanger and the outdoor unit. So you see the standard trim here. We combined air, dirt separator, flow switch, circulator, purge valves, isolation valves out here if we ever have to remove that unit. We have a separate circulator that takes the heat into the buffer tank. The temperature in that buffer tank is being monitored by an outdoor reset control. And the outdoor reset controller is set up to operate on this blue line here. And what it does is it determines how warm that tank gets based on how cold it is outside. If it's a design day outside, we might get up to 110 degree water temperature in that tank. But if it's 30 degrees outside, we might get up to only maybe 97, 98 degrees. The idea here is don't heat the tank any warmer than necessary so that the water supplied from the tank to the distribution system can adequately heat the building. So the lower we can keep the water temperature in the buffer tank, the better the performance of that heat pump is going to be. Now, the distribution here, it says zone radiant ceiling panels. Again, it could be radiant walls. It could be any of those heat emitters we've talked about, but a lot of zoning. I'm showing separate thermostats here. So our buffer tank is preventing short cycling of the heat pump based on having a very diverse situation. So we just lost our connection here, I guess. See if we can get back here. If you can still hear me, bear with me. Here we go. Mark, can you see it okay?
Yeah, we can hear you, and your screen is up. And
okay.
It doesn't show it in presentation mode. Oh, there we are.
There it is. It's back.
We're back. Okay. Not sure what happened there. The tank is serving as a buffer tank. It's also acting as a hydraulic separator between the circulators. And a little detail right here. This is a on-demand domestic water heating detail with another stainless steel external heat exchanger. And let's say that we get a demand for domestic hot water. We're going to turn on the circulator, and we're going to take warm water from the top of that buffer tank, send it down through this heat exchanger, and at the same time, we're going to be passing cold domestic water in the other direction through the heat exchanger. Now, the temperature rise we get will depend on the temperature in the tank. If the tank was up at 120 degrees, and this was a generously sized heat exchanger, we might come out of here at 110 degrees. If the tank is only at 85 degrees, obviously we aren't going to come out of that heat exchanger anywhere near the temperature we need to deliver to the fixtures. So we're going through a small thermostatically controlled electric tankless water heater. And that'll provide the boost. The modern versions of these are set up with thermostatic controls. They will only operate the heating elements at the wattage necessary to take whatever preheated water temperature comes in and boost it up to that desired set point temperature. Now, controls, you can take a look at this later. This is essentially a ladder diagram. It might look complicated, but when you study it, it's really a pretty simple idea. We've got independent thermostats here that operate standard zone valves. The end switches in the zone valves come down. They turn on the outdoor reset control. When there's a demand for heat, that outdoor reset control takes a look at the temperature in the tank. It makes a calculation based on this graph. If the tank needs to have heat, it turns on the necessary devices to add heat to the tank. If the tank's already warm enough, those devices stay off. And it also manages the distribution circulator. So it's an these are all off-the-shelf components. This is an easy system to put together today, and it's a good example of tying an air-to-water heat pump in with hydronics. Here's one other one. Taking a look at the clock here, I'm going to move a little faster. This is 2 zones of chill water cooling combined with multiple zones of hydronic heating. It does use a buffer tank. We have that same detail here for domestic water heating, but we're also tying in an auxiliary boiler. We're tying that into the upper portion of the buffer tank so we can get some buffering effect, but we don't want to heat up the entire tank. This, by the way, is assumed to be a 2-stage air-to-water heat pump with the lower stage such that it matches capacity with one of these air handlers. And that's why you see there's no buffer tank between these 2 air handlers and that unit, because it's a 2-stage unit. If this was a 1-stage unit, we would probably not use this schematic. We'd want to have a buffer tank involved during the cooling mode, and again, that's to protect that heat pump against short cycling in cooling. Let's jump over to water-to-water geothermal systems. Again, I won't spend much time on this. The standard refrigeration cycle. We have a very nice, neat installation here. This is a water furnace unit. We're going to take a look at this manifolded earth loop configuration later. But you can see that's piped over to a Caleffi Thermocon buffer tank. And then from there, we go off to multiple circulator-based zones in the system. Heating performance, same story. The warmer the earth loop can supply fluid to the heat pump, the higher the heating capacity and the higher the COP. Where we come in is in terms of designing the earth loop. More piping means higher temperatures. Now there's calculations and software to get you to those numbers, but in general, larger earth loops are preferred from a performance standpoint because they do keep that water temperature higher. The other thing we control, again, is entering load water temperature. This is the water coming back from our heating load, entering the heat pump. The lower that temperature is, the higher the capacity and the higher the COP. So always remember temperature lift between the evaporator and a condenser. Whether it's an air-to-water or geothermal water-water, it's the same story. The smaller you can make that temperature lift, the better. Okay? On the cooling side, very similar. The warmer we can operate our chilled water cooling system, and the cooler we can keep our earth loop in the summer, the better the cooling capacity and the higher the energy efficiency ratio. Again, if you get the archive file, you can take a look at these and get specific numbers off of them. Here's a buffer tank. It's a similar idea where we have multiple zones. We have an on-off water-to-water heat pump supplying heat. We're putting that buffer tank in between to act as a mediator between the output capacity from the heat pump and what the load could be at some point. And it's also, again, functioning as a hydraulic separating device. This is a geothermal install with, again, using the Caleffi Thermocon tank. Basically, the heat pumps are over on this side, and then we're distribution over on the right side here. When you're using a heat pump, a water source heat pump like this, good idea to use vibration isolating connections between the heat pump and any rigid piping. This is a reinforced hose assembly that several companies offer, and nice detail here where the installer puts some unistrut type rail up, and then you can see he's got a nice relief bend in those to isolate any vibration from the heat pumps to the rigid piping. Electrically, there's a couple things to remember with heat pumps. When we operate a heat pump in a heating mode, we're going to use the internal 24-volt signal that's generated by a transformer in the heat pump. We have to connect that to the Y terminal. That basically turns on the compressor and allows that heat pump to function in the heating mode. Okay? When we want to operate the heat pump in the cooling mode, we've got to do the same thing. We've got to take the 24 volts from the R terminal, get it over to the Y terminal to turn on the compressor. We also have to take 24 volts to the O terminal, and that energizes the reversing valve, and that forces that refrigerant to pass through the refrigeration system so that the machine is operating in a cooling mode. And there's different ways to do this. This just kind of shows a generic way to do it. Here's a way to do it with an external relay. Basically, if we have some kind of a contact closure that represents a heat demand and another contact closure that represents a cooling demand. We can work in this relay here, and the relay basically takes care of providing the logic that we've talked about over here. Okay, open loop.
Hey, John.
Yes.
A question came in on, speaking of the wiring on a heat pump, in terms of buffer tank sizing. Is there any rules of thumb for how frequently you want that heat pump to cycle on and off in your buffer tank sizing?
Yeah, again, I won't say it's scientifically researched, but I'd like to suggest minimum of 10 minutes. Minimum of 10 minutes. Manufacturers, you could certainly ask them if, but you know, if you look at 10-minute minimum cycles and versus 5-minute cycles, 2-minute cycles, it could be several thousand start-stops over the course of a season or a year. And as with any device, any motor, the more you're starting and stopping it, the shorter its service life is going to be. So I would suggest 10 minutes as a starting point, and possibly take a look at this formula and maybe experiment even with 15, 20 minutes and see what it does to the volume requirements of the tank.
Thank you.
Okay, open loop systems where we're using groundwater from a well. Real quick, two things: water quantity and water quality. You have to make sure the well is tested to have adequate output. When I say tested, you should have a certified well driller do a drawdown test, have a piece of paper that documents what that well can produce. And then water quality. Very important. We don't just pump what comes out of the ground regardless of what's in that water through our heat pump. A lot of people have tried that, and a lot of people have run into problems with that. Manufacturers of heat pumps typically put out a minimum groundwater quality specification that lists things like total dissolved solids, pH, hydrogen sulfide content, and so forth. This one happens to be from Climate Master. Make sure that the groundwater that you're considering for use for the heat pump meets, as a minimum, what the manufacturer requires. Now, going over to closed loop systems, again, we could be talking all day about different loop configurations. I've shown a few common loop configurations for horizontal trenching down here. Up in the upper right, here's a slinky field, probably a nominal 5-ton slinky field here with one of these slinky coils per ton. They're external manifolded. This is all either fusion, socket fusion, or perhaps some butt fusion joints. Here's a wider trench. This is actually PEX A tubing that Rehouse supplied. So there's many different ways to put this piping in the ground. Here's a vertical installation. You can see this can get a little dirty. Imagine this on your typical half-acre suburban lot. Imagine what your neighbors are thinking when they take a look at that. It's not for every place. But oftentimes this is the only recourse when you have very limited land area. The photo down here shows several vertical bores that the pipe's been inserted and regrouted, and you see the connections off here to the manifold piping. The piping that is most commonly used is high-density polyethylene. It's joined together using butt fusion. Here's a butt fusion machine that creates a joint like this. Or socket fusion. Socket fusion uses a socket similar to a socket on a PVC pipe or a copper pipe where the tube inserts inside the socket. And there's different equipment for socket fusion. Here's some headers that have been built up with socket fusion. But I want to convince you that it's not always a pretty picture in an earth loop trench. I'm sure some of you have been in trenches as I have. I've actually had a trench partially collapse on me. Learned a good lesson. Fortunately, from the hips down, I was able to get out of it, but this is a mess, and you can imagine trying to get in here, clean these pipes up, and do this fusion. So is it possible to put an earth loop in without doing this fusion out in the trenches? And the answer is yes. You can do what's called a manifold-based earth loop. Caleffi does provide product to do this. It's a specially designed product, a high flow rate manifold system, modular system. And basically, you put this together based on how many earth loops you're going to need. And with the right design, you can buy tubing in 1,000-foot coils. It's very possible to put earth loops in without having to have any fusion joints out in the field. So that completely eliminates the equipment and the work to do that. It also eliminates things like reverse return piping and stepped pipe sizes in the external manifolds, because there are no external manifolds. You're basically bringing all these loops inside the building and tying them into a manifold. Very similar in concept to what you would do with radiant floor heating. Okay. One big advantage that I see with this type of a system is when you have isolation valves on each circuit, you can fill and flush each circuit independently, and that's a much lower pumping requirement. Flow rate and head is much smaller. You can do that with a smaller submersible type pump as opposed to perhaps a 2 horsepower swimming pool pump. Okay. You can get these manifold systems with flow balancing valves on each one of them, so you'll know what's going on within each earth loop. You can see here it's a very modular system. Put it together as you need it. Here's an example where the tubing comes in through a foundation wall. It's very important you do a good job sealing that penetration. Just pumping a tube full of GE silicone in there is not a good seal. We like to use these link type seal products. These are compression seals. The pipe basically passes through that inner space. This is a 2.5-inch core drill hole through the concrete. Tighten up these bolts and you get a nice tight seal there. Caleffi also offers elbows that are ideal for situations like this where we want to do a quick 90-degree change in direction. And here it is looking straight in, where our elbows would make that transition and we go right up into our manifold type system. So this way there are no fusion joints outside. Everything is inside the building. Nice, neat system. There are many products on the market for flow centers. Here's a couple of the latest products out from a company called Geothermal. They do offer one with a high efficiency ECM-based circulator. That can be variable speed based on the temperature differential in the earth loop. You can check that out. Here's a nice setup, hydronic setup for an earth loop. I'm a firm believer in having expansion tanks in earth loops because there are significant changes in volume as the temperature changes from summer to winter operating conditions. Hydronics number 9 goes into a fairly lengthy discussion that shows you how to size an expansion tank for this type of an earth loop. And a good combined air and dirt separator. Obviously, when you're putting piping in the ground outside, there's a good chance there's going to be some dirt in it, or insects, or whatever. So a good air and dirt separator will help get that debris out of the flow, get the air out of the flow before it gets into the heat pump. And I firmly convinced the future of geo heat pumps is going to be tied to ECM-based high-efficiency circulators. We really don't want to use hundreds and hundreds of watts in a residential system, maybe even 1,000 watts, just to move the fluid through the earth loop. And there actually are products out there that approach 1,000 watts to do that. So a high-efficiency circulator and a speed control circulator is going to bring that down. Real quick, here's a schematic that shows zoned heating and cooling. And you'll see both the heating over here, which is grayed off right now. We're assuming we're in a cooling mode operation, so the heating's grayed off. Here's our zoned chill water air handlers. They are being supplied through the buffer tank. The heat pump can switch between heating and cooling mode. And another detail that is shown is a little de-superheater coil, sometimes called a hot water generator, that several manufacturers build into their heat pumps. This takes the hottest refrigerant gas right off the compressor, steals some heat from it without causing it to condense, and uses that heat to preheat domestic hot water. So heating, cooling, and domestic hot water preheating coming off of that system. Here's another system. This is doing zoned heating using panel rads that have been sized for relatively low temperatures. Here's that on-demand domestic water detail. Buffer tank. Single zone cooling. Single zone cooling combined with multiple zones of heating is a fairly common situation. You'll notice that chill water air handler is not drawing from the buffer tank. We're assuming that chill water air handler has been matched up to the cooling capacity of the heat pump fairly well, so we aren't going to get into short cycling situations. And again, manifolded earth loop, the same type of details that we've talked about. And I think that is it. So, Bob, I'm going to go back to you to close this out.
Yeah, that was a mouthful. Thanks for that. It was a lot of great information, and we will make these slides available. I know there's a lot of questions as we went through here. Mark's going to try and get to a couple of them here. You know, people can stay online as they would like. I'd like to thank everybody that did show up today. I think it was our record breaker. I think we're approaching 1,000 people. We're going to melt down the GoToMeeting server here somewhere if we keep going at this rate. But a couple housekeeping things, and then we will hit some questions. Mark's been saving up some of the good ones here. We'll get to everybody's questions, of course, but probably not on the presentation. We'll answer them via email, so we'll get to everybody. Give us a little bit of time to do that. There was quite a few questions. But coming up, I'll be doing the next one, heat migration to hydronic systems, coming up in June. We've got the rest of our schedule posted on our website, so if you go to caleffi.us, you can look at what we've got figured for the rest of the year. John's going to rejoin us in December and January of 2015 for some good pump sizing information. Some of those pump curves and schematics that you saw, we want to explain how that works, how you match a pump curve and a system curve. So that'll be a good one to get on your must-see list. So let's see what else we got here, John, for slides. Caleffi Excellence, you got a couple more days to get your entry in and win a prize and possibly a trip for you and a friend to Italy. So if you've got a design or a job that you want to get in, the clock is ticking, as we say there at the bottom. So one of the past winners there, that Bruce Fall from Shamrock Sales, I know he's online today, took one of his customers over, and they had a great time over in Italy. So follow us. We're trying to cover all the bases here with social media, Facebook, Twitter. We're out there everywhere. We're here to answer questions. We've got a great staff, so we'll get to you if you have any questions on this or any other product questions. Just call us or however, email us, however you want to get a hold of us. We will have this. Now, you have to answer the survey to get the certificate. There'll be a couple questions on a survey that should come to you right after you log off of the webinar. Now, sometimes if you got a lot of things open on your computer, it's layered in there. People say, well, I never saw the survey. Well, you didn't send me the survey. Well, we did send the survey, but you might have to close off some of your things and find it layered in there somewhere. If not, certainly get a hold of us, and we'll make sure if you need a certificate or want a certificate, we will, in fact, get that to you however we can. So I think is that about it on housekeeping, and then we'll have Mark do a couple questions, and hang on as long as you want, and we'll get to a couple questions. And what do you got there, Mark? Yeah, we've had a number of questions coming in. We've been answering them. One thing. Wait, one thing. Siggy's got a new book coming out. This is a great one. I've seen some spy photos of this on the right-hand side there. It's coming soon. Heating with renewable energy. It's going to be a lot like his modern hydronics, but it's going to be all in renewable energy, solar, geo, wood, pellets. It's going to be great. All right.
Okay, for the audience, we'll just limit this to 2 questions. One question, John, you talked about preheating domestic hot water when you're using whether an air-to-water or water-to-water heat pump. Is there any situations you can think of where you would not want to preheat hot water if there's a building requirement for it?
Whenever you have a domestic water load, you've really got a good situation. And the reason I say that is that domestic water heating, you start with cold water at perhaps anywhere from 45 to maybe 55 degrees. So if you've got heat available from a low temperature source, you have the temperature differential. Even if you had 85 degree water in that buffer tank, you can still transfer heat into, say, 45, 50, 55 degree water. And displacing energy at the low temperature end of the spectrum is you're saving just as much as you are displacing energy at the high temperature end of the spectrum. So anytime we look at these systems, what we call Combisystem, we're always looking for that domestic water load as something that is I'll call it a priority load. We're going to try to send energy into that because we can do that with even moderate water temperatures. As I say, 85, 90 degree water in a buffer tank. If that's all you need for space heating on a mild spring day, you can still get perhaps half of your temperature lift for domestic water accomplished with that temperature. So definitely use domestic water preheating whenever you can.
Thank you. Another interesting slide is when you did a comparison on similar systems using air-to-water and water-to-water heat pumps. Mm-hmm. Would you get different results, would you expect, if you also had the need for cooling on an apples-to-apples basis?
I think you'd probably see similar results. In a deep southern climate where you've got a long cooling load, I would expect the geothermal system will outperform on a EER basis the air source system. So you could run I ran just a heating load analysis in a situation where you've got both heating and cooling loads. The software from the manufacturers that I use will do both of those. So you would run a year-long basis. I suspect, again, that the geothermal would outperform the air-to-water heat pump on a cooling load basis in most situations. Perhaps in the far north, maybe not, because you have, first of all, you have a very minimal load, and you really don't have those 90 and 100 degree temperatures very often. But again, the bottom line is not COP. The bottom line is kilowatt hours, the difference kilowatt hours on a seasonal basis, and how do you take that difference in operating cost and use it to amortize the difference in installation costs? That's really the bottom line on it.
Thank you. And lastly, since it looks like we still have about 80% of the people that were on the front end of this, would you hazard to offer up any, what are maybe the key design considerations or gotchas when it comes to a designer laying out a air-to-water system and a water-to-water system? Any major issues that frequently come up?
Yeah, definitely. And most of them are usually on the balance of the system. Hopefully most people, if they're doing geothermal heat pumps now, are perhaps ICSPA certified or have been trained or assisted in designing the earth loop. But I'll give you a good example of a common error, is putting in some type of a radiant panel system that is not capable of operating at those low water temperatures. Stapling the tube to the bottom of the subfloor without plates, stapling the tube to the side of the floor joists, bad idea with any kind of a heat source. And you could have a great heat pump and a great earth loop and have a disaster as far as the system is concerned when you have the inability to get that heat out of the water at relatively low water temperatures and transfer it into the space. So stay away from staple up, stay away from especially plateless staple up type radiant systems with any type of renewable source, especially a heat pump.
Okay, John, thanks a lot. We have a number of individual questions we'll follow up one-on-one, so I want to thank you on behalf of Caleffi. And Bob, I'm going to send it over to you to wrap up.
Yeah, thanks, everybody. I know there's a lot of questions. People want the slides. We will get those out. Again, we've got quite a list of people here today, so it might take us a day or two to get you. It will be archived, the whole presentation, on our webinar. That takes a couple days, too, because we've got to change the format from the YouTube format or from the GOTA format to